inaugural lecture of the lecture series in line with University of Moratuwa Research Week 2023. University of Moratuwa Research Week 2023 has been organized for the third consecutive year, and the theme of this year is connecting academics, practitioners, and the society in order to shape futures through advancing multidisciplinary collaborations. So again, it's a great pleasure to have you all here with us today. And without wasting time, I'd like to invite Professor Tishanja Singha to introduce our lecturer for the day.
Good morning, ladies and gentlemen. It's a great pleasure to introduce one of my brightest students, Professor L.I.N. Silva. I first came across L.I.N. somewhere around 1996, and that was the time he came to University of Moratuwa. And then in 2001, he graduated with first class honors, being the batch top at final year and overall batch second from a batch of 100 students. So those days, we used to coordinate the finding employment, because we wanted to make sure the students get employment within 1 or 2 months of completing the final year. So one day he came to me, asking whether he can join Central Engineering Consultancy Bureau. So then I asked, okay, what are you going to get? And he has said, I'm going to get a first class. So I have said, there's no way you go to CCB. You continue your education up to MSc and then up to PhD. So he took the lead. By 2004, he finished his MSc at the very prestigious Tokyo University of Japan. And then immediately after completing his MSc, he found employment in United Kingdom as a design engineer. And that was the time, after a few months of that, he actually found he was lucky to be selected to read for PhD at the very prestigious Tokyo University. Tokyo University is a place where a normal Japanese person cannot join. It's a very highly regarded university in Japan, ranked number 1 in Japan. So after graduation, after obtaining his PhD in 2008, Dr. L.I.N. Silva was absorbed to our staff, and since then he has been working and recently was promoted as a professor. And as Professor Priyanda has said, professors are supposed to find knowledge. And he has, with Professor Amar Singh from Mechanical Engineering Department, he has developed a pressure cell that can be used for piling testing work, and they have patented that. So, and also Professor L.I.N. is a brilliant engineer, and whenever we are involved in tall buildings or large structures, we seek his expertise. And he has mastered the very special category of engineering called value engineering. The idea of value engineer is to review the design of a good engineer and reduce the cost by 20% or 30%. And Professor L.I.N. is a master of the game. For example, a normal engineer might say, when we do a pile of 1200 diameter, the load carrying capacity is 6000 to 7000 kilonewtons or 600 to 700 tons. But when it comes to Professor L.I.N., the same pile will, with some modifications, will carry 10,000 or 11,000 kilonewtons or 1000 or 1100 tons. And that means instead of using 2 piles, now we are using 1 pile. And we knock off 20 to 30% of the cost from the project. So which means from a 500 million rupee piling job, the moment the client comes and contacts or the Professor L.I.N, it will become a 350 million project. So that's the brilliance of Professor L.I.N. So I cordially invite Professor L.I.N for his inaugural lecture.
Very good morning to all of you. And first of all, I would like to thank our head of the department and Professor Tishan Jayasinghe for his kind words. So today I'm going to talk about a very special topic, something that fascinates me from my childhood. It's about handling stresses. I'm going to talk about on how the humans and the area that I am familiar with, that is the soils, geotechnical engineering, are closely linked to each other in terms of handling stresses. So this the inspiration to talk about this topic came from, I would like to talk about some background, my background. Actually, I was born and raised from a very famous village in Sri Lanka, Angod. So my home was about 20 meters, 30 meters away from the National Mental Health Institute, and my father used to work there, and my mother was attached to the IDH hospital. And I'm really happy to see one of my neighbor is sitting next to me, Mr. Nishan Punchieva, our acting librarian. We were neighbors. So, and I frequently used to visit the institution, and I was so fascinated about the mental health of people. And actually I was, during my O-levels and A-levels, I was so interested in psychology, and I wanted to become a psychologist. But later I found that I am somewhat good in mathematics and ended up being a civil engineer and finally a geotechnical engineer. So when this task is vested upon me, I was planning to discuss about the work that I do in geotechnical engineering. I thought the best way to do is to link it to ourselves, because when you study or go deep into the soil mechanics, the fundamental behavior of soils, and you will realize that it is closely linked to the behavior of humans. So I would like to discuss few aspects of soils and human behavior today. So let me categorize my talk into 5 subtopics. How the soils and humans respond to small stress cycles. So today I'm talking about stress. Stress, when it comes to soils, I am talking about the physical stress, that is the force divided by area. For humans, I am talking about the mental stress. Okay. So when there are every day we are encountering small stress cycles, and we respond to those stresses. So that is the first thing I'm going to discuss. Then when the stresses are getting increased, soils are also getting close to a peak. We call it the peak strength. And the behavior of soils close to the peak or before the peak has something similar to the behavior of humans when they are stressed close to the peak. Then how the humans and soils would behave during cyclic loading. The loads are applied, or the stresses are applied in cycles. And if we during these stress cycles, some people or some soils behave in undrained manner. Some soils behave in a drained manner. Similarly, humans also take the stress without releasing their the stress. So they take the cycles, they undergo the cycles without releasing the stress. It's very similar to undrained cyclic loading of soils. So I'm going to talk about that. Finally, I would like to discuss about what happens to the soils as well as humans after we exceed the peak, after we fail. And both soils and humans have a remarkable characteristic called thixotropy. That is gaining the lost strength over time. So these 5 aspects will be discussed with some of my work and some of my colleagues' work on the related areas. So let me first discuss about the small cyclic loading. So basically what I'm going to do is I will take you along a journey of this curve. This is the y-axis is the stress and x-axis is the strain. In other words, it's like the damage to the soil sample. Strain means damage. So a typical stress strain curve is given of soils is given here. When you start loading, it will load. It's a highly non-linear behavior like this. And if you are stressed and if you leave it there, soil will continue to accumulate strain, damage. That's called creep. Any other material would behave in a similar manner. Then when you have sudden change in the loading rates, if you are suddenly given a deadline, you will see some a response. Soils also have a similar response. And if your stress is suddenly released a little bit, another response. So loading rate effects I am going to discuss. Then finally peak and after peak, post-peak behavior. Right, to start with, let me compare that curve, the previous curve, with the performance curve of the humans. So this, some theories have been developed by psychologists. So they say that the performance of the humans, it depends on the stress level. When the stress level is low, so we are in the laid back phase, lethargic, right? Fail to initiate something. Then there is an optimum stress zone where we perform really well. And if we are overstressed, then we will enter the exhaustion stage. Similarly, the soil will enter the critical state. Then finally, we undergo failure, mental diseases, health problems, and finally, breakdown, right? Mental breakdown. Similarly, soils will have the residual state. So this is another similar graph. So the psychologists define these zones as hypostress, eustress. Eustress is the zone where the humans behave with optimum performance. And distress. I hope you all know what is meant by distress. Right. So the psychological stressors, the events that cause stress on humans are categorized into 4 different types by the psychologists. First, crisis or catastrophic stress events, that is devastating natural or man-made disasters like landslides, floods, earthquakes, wars, pandemics, and so on. So this, the behavior of humans under this kind of catastrophes is quite similar to the peak or post-peak behavior of soils. I will touch upon that. Then comes major life events, marriage, going to college, death of a loved one, childbirth, and so on. So you will be stressed not to the peak, but close to the peak sometimes. Then there are daily hassles or micro stresses, we call them. attending a meeting, making a decision, they all cause some stress on us. So it's like small cyclic loading of soils. Then finally, ambient stresses, the stress that comes from the surrounding. We call it the peer pressure. Okay. And finally, I will discuss about the thixotropic behavior, that is after the breakdown, still the humans and soils can recover, gain its lost strength with time. So let me first start with the small cyclic behavior. In order to investigate the very small cyclic behavior of soils, I have involved in the development of sensor system during my master's degree. So this system is based on what you see in the background is a soil sample, and these are 3 sensors. This one is capable of measuring the vertical deformation. This is measuring the changes in the diameter of the soil specimen, and this is measuring the shear. So with this system we can measure the 3 components of strains in a soil specimen. And it is based on the principle that, you know, when this kind of it's made of Prosper bronze strip, right? Prosper bronze is a material, Prosper bronze strip, and at the center 4 strain gauges are fixed, glued to the strip, and it is wired. Wiring is done to create a Wheatstone bridge. Okay, I hope electrical engineers are quite familiar with this Wheatstone bridge. So when this strip is deformed, the output voltage is affected by the deformation, by the bending strain of the strip, and we can calibrate that with whatever the movement of the 2 ends of the strip. So this technique was first developed in at the Tokyo University, and I have utilized it to measure the 3 components of strains like this. And later I have modified it by separating the 3 like this. In the previous one, the hinge is common. It's very difficult sometimes to have a common hinge in a cylindrical soil specimen. So what I did was I have modified it to have separate hinges like this, but still I can get the same results. Then I use this system to investigate the very small cyclic behavior of soils, and I'll show you a typical stress strain curve. This is a shear stress. Shear stress is applied by applying cyclic shear stress on the soil specimens, and this is the corresponding deformation strain, and you can see the stress strain behavior is highly reversible. Although the soil stress strain curve is nonlinear, at very small strains it shows perfectly elastic behavior. So this is another figure. You can see the general stress strain behavior and the small cyclic loading. So when the soils are subjected to small cycles, it shows a very stiff response compared to the general stress strain. So the gradient of this curve and the gradient of that curve are totally different. This is a very stiff or strong response. And this is another test data. When you increase the cyclic amplitude, right? When you increase the amplitude of the cyclic loading, the damage starts to accumulate. It's not perfectly elastic. You can see the strain keeps on accumulating with the number of cycles. So the same thing happens to humans. Now let me move into the topic of the humans, how the humans would behave under this kind of loading. So The daily hassles are small events. They are small but frequent events that happen throughout our day, and they directly result in stress. So research has found that these daily hassles better predict the mental health of a human than major life events. So they are a big source of stress because we encounter them quite frequently, and depending on the amount of the stress cycle that we undergo, the damage can accumulate and cause problems in the long run. So a psychologist has developed the daily the hassles and uplift scale. I would like to show this. It consists of 53 items that measures people's attitude towards various aspects of their lives on a daily basis. So it basically assesses the behavior of humans under small cyclic loading. So, sorry. This is the hassles and uplift scale. And they suggest that take this test before you go to bed every day, if possible. There are 53 life events. Your children can be a hassle for some people, and it can be an uplift for some, according to the psychologists. Your parents-in-law, your relatives, your spouse. So they have listed 53 such items. I'm not going to go into the details. 53 such items, and you have to give a rank from 0 to 3, whether the left hand side is a hassle, right hand side is an uplift, and you can count the total and decide on the effect of these hassles on your day-to-day life. Then the soils have a very interesting characteristics. It will learn from experience. When you load a soil sample to a certain stress, it remembers that stress. We call it the pre-consolidation pressure, the technical term. Then if you unload it, soil always remember that, okay, in the past I was loaded up to that particular stress. And when you load the soil specimens again up to the previous maximum stress, soil shows a very stiff response because it has already experienced the stress. And beyond whatever the maximum past stress, it shows a weaker response. So this is very typical stress strain behavior. So previous maximum stress, always the soil specimens remember. Then when you unload, it shows a stiff response, and if you keep on loading beyond the previous maximum stress, it shows a weaker response. Sudden change of the gradient can be seen. Then about the creep effects. So I would like to discuss my second topic, that's the pre-peak behavior, the before peak. I'm going to talk about two things, creep effects and the loading rate effects, and how they are linked to the human behavior. The creep effect means you apply a stress and maintain that stress for a certain period, and you will see the accumulation of damage in the soil specimens. That can happen due to various reasons. Particles can rearrange, or particles can even break because they are already loaded, and it can cause some damage and accumulate some damage. And if you start loading, after waiting for some time, if you start loading it again, it will show a very stiff response. Right? Same thing happens to humans as well. Then comes the loading rate effect. This is stress strain curve. During the loading of this soil sample, right, the loading rate has been changed. So 1/10 means there is an original loading speed, then the speed has been reduced by 1/10. Then it is loaded at that particular speed, and suddenly the load has been, the loading rate has been increased by 10 times the original, 100-fold difference. And you will see sudden jumps in the stress strain curve, right? Same thing happens to humans. So if you are under a certain stress, and let's say you have a certain deadline, so you are working on something, you have a certain deadline. Let's say suddenly you are informed that your deadline has been reduced. Tomorrow you have to submit, right? Then you will start working hard and you will show a stiff response. Similarly, if the deadline has been postponed, you will see a relaxation, right? Relaxation of stress, and finally it will join the original stress strain behavior. So this is Holmes and Rahe stress scale. Is a tool developed by Holmes and Rahe to assess the effect of this kind of large loading events on your health, mental health. So they have categorized some life events, major life events that might cause stress on humans, and assign some life-changing units. So this is developed after doing a lot of studies. I am not going to go into the details. And they have published so many papers on that as well, after doing so many case studies. So you can see the life-changing units for different stress events, right? Imprisonment, divorce, marriage, likewise. And so if you undergo some or few such stress events, you can count the total life change units. And according to this classification, if the total life changing units is more than 300, you are at risk of illness. It's like close to failure, right? So some classification of the mental health based on these life events has been developed. So I'm not going to go into these events. If you are interested in this, I can share this later. Then I would like to discuss about the behavior of soils and humans when they are subjected to cyclic loading. This is one of my major areas of interest. I have been working on the cyclic loading behavior from my PhD. So soils are subjected to stress cycles due to various events like traffic loading, sea waves can cause loading cycles, earthquakes, and then explosions also can cause loading cycles. And during this loading, it can be a cyclic loading, it can be a single direction monotonic loading. Soils have a very interesting characteristic called drainage condition, because you know soil is an assembly of particles with voids, interconnected voids. These voids are either filled with air or water or maybe completely empty. So if the voids are completely filled with water, we call such soils as saturated soils. Then when you load a soil sample, this water is initially taking the load, and then water will release its pressure. So this water is very similar to the emotions of humans. So if the water pressure is allowed to release during loading, we call such loading conditions as drained loading. If water is not allowed, water pressure is not allowed to release or dissipate, we call such loadings as undrained loading. Okay, so drain loading strengthen the material, and undrained loading weakens the material. Same thing happens to humans as well. So let me elaborate this a little bit. So, sorry. If undrained loading happens in cycles, the soils can undergo a phenomena known as liquefaction. This liquefaction it means finally soils starts behaving like a liquid. So that is what is meant by liquefaction. So let me further elaborate you on this, what is meant by liquefaction. And liquefaction is it mainly occurs in sandy soils, right? Ground with mainly consisting of sand. So what happens is, during very sudden loading, it can be an explosion, it can be an earthquake, mainly due to an earthquake. What happens is, water pressure quickly rise, and if water pressure cannot be released, right? The pressure cannot be released during the loading. What happens is, particle to particle contact stresses will be lost, and soil starts behaving like a liquid. So that is what is called liquefaction. Let me show you a small video to demonstrate this concept. So this is a foundation placed on sand, and you can see it is shaken by giving an earthquake motion. And what happens is, there is no time for the release of water pressure. As a result, this foundation simply sinks into the ground. And this is what happens during liquefaction. These photos are taken during the 1964 Niigata earthquake. You can see this is an apartment complex. Some buildings are on pile foundations. Some buildings are on shallow foundations, not on piles. The buildings that were not on pile foundations failed during this earthquake, mainly due to liquefaction. And something interesting happens during liquefaction. This kind of the structures that are very heavy simply settle, or it can even topple during the earthquake due to liquefaction. And these closed structures like manholes, they are uplifted, because when soil behaves like a liquid, it will apply an upthrust. The increase in buoyancy cause this kind of closed structures to be uplifted. So there can be a serious damage due to this. Most of the lifelines like electricity or drainage lines are uplifted, while the buildings settle, the connections are lost. So severe damage. And I'll show you a video. So this video is recorded during the same earthquake. It is one of the very few live liquefaction earthquakes available, other than the demonstrations I have shown. So he came to the Niigata airport for a private trip, a professional photographer, and the earthquake struck while he was waiting to get on board. And the soil near the airport building liquefied. Within 30 seconds, the building starts to settle. So this is what happens. You can see the quality of the video is not very good because it was recorded in 1964. But you can clearly see now the earthquake is happening. You'll be able to see water coming out, and the building starts to settle slowly. And within 30 minutes, almost half of it's a 2-story building, half of the building is has settled, more than 1 meter settlements. So people got panicked and they are running. You can see water coming out, right? So now the drainage is happening, but the damage has already happened by that time. When the earthquake happens, there's no time for drainage. So water pressure suddenly goes up, particles lose its contact, and soil starts to behave like a liquid. So let me discuss this in further detail. Now what happens when the soils are subjected to drain cyclic loading, and what happens when the soils are subjected to undrained loading, like what happened during the earthquake, right? So when the soils are subjected to drain loading, drain means water is allowed to go out from the soil samples. So I will show you some typical stress strain curves of two cases. First one, the stress cycles are applied in constant amplitude like this. Second one, stress is applied in increasing amplitude. The stress amplitude keeps on increasing. So what happens is, when you apply constant stress amplitude, so this is 60 kilopascal is the amplitude, minus 60 you are applying in both directions, cycles. So what happens is, this is the behavior, stress strain behavior during the very first cycle. Number 1 means first cycle. This is the second cycle, third cycle. So soil is getting stiffer and stiffer, and in the meantime I am applying small cyclic loadings as well. I just want to show you that it's perfectly reversible and elastic behavior, and very stiff compared to the general behavior. So okay. So what happens is, this is the stiffness during the very first cycle, second cycle, third cycle. So soil is getting stiffer and stiffer with the number of cycles. Keep in mind that the drainage is always allowed. Water is going out during these cycles, stress cycles. And this is the density. What happens to the density? dr is the relative density of the soil. So density is increasing with the number of cycles. So it's moving in upward direction, means soil is becoming more and more dense. And if you do the same thing with increasing amplitude, the stress amplitude is increasing. First I apply a small cycle, then a little bit larger cycle. Again drainage is allowed, but soil is getting weaker. So in the beginning very stiff response, but with the increase of the amplitude, stress amplitude, soil starts to dilate or loose. Getting this side is dilation, means it's becoming loose. Soil is getting loose. So if you want to increase the density of soil or compact soil, it's always good to apply whatever the load in constant amplitudes under drain condition. Then it's getting denser. Then what happens to the same under undrained condition? So in this case, water is not allowed to drain. So I have applied stress, relatively smaller cycle, then it's increased to 40, 30, 40 and 60. So 3 different amplitudes of constant amplitude cyclic loading, but water is not allowed to drain out from the soil specimen. So let's see what happens during this. This is what is causing the liquefaction. So let me first explain the right hand side figure. So the x-axis is it represents the mean effective stress of soils. That means, in simple words, it's like the average interparticle contact stress. Particles are in contact within a soil specimen. So this stress at the beginning of loading, there is about 100 kilopascal average interparticle contact stress. When you don't allow drainage and start applying loading cycles, this 100 is getting less and less and less, and finally it becomes 0. So this is where the liquefaction takes place. Soil starts behaving as a liquid here because particles don't have any contact, 0, right? And it will enter this kind of, we call it the cyclic mobility of soils. So when there is no shear stress, it behaves like a liquid. When you apply some shear stress, it gains some strength. When you unload it close to the 0 stress, it behaves like a liquid. When you come to this particular state. And this is 30 kilopascal amplitude. And when you increase the amplitude, soil becomes a liquid quite fast. And you can see there about several cycles are needed to bring the stress down to 0. But when you increase the amplitude, it comes to 0 within less number of cycles. If you further increase, even one cycle is enough to cause. And if the soil is very loose, you don't need cycles. It will become a liquid with single stage of loading. This is what happens. This is very loose soil, relative density 21% means very, very loose soil. Starting from 100, if you apply single cycle, it becomes a liquid. So this is a very important aspect of soils in reclaimed lands like Port City. Port City is made by reclaiming the soils from the sea, and it is dumped using different techniques and then compacted to various degrees. But if an earthquake happens, liquefaction is a prime concern. So they have taken special measures to make sure that the structures in the port city are safe against a design earthquake. So this is one of my major research interests. I was given the task of modeling this behavior. This is one of the most complicated behavior, soil behavior, undrained cyclic behavior of soils. So modeling this is like a nightmare. So during my PhD and after my PhD also, after I came back to Moratuwa as well, I continued this area, and I developed a model capable of simulating this cyclic behavior. The bottom figures are the simulations using the model that I have developed. So I'm not going to go into the technical details. You can see that we can reasonably model the cyclic behavior. And this model is even capable of modeling this kind of behavior of very loose soils where you only need one cycle to cause liquefaction. Then I would like to jump into the human behavior under the cyclic loading. So cyclic stresses. So some stresses are positive stresses and some are negative stress cycles. So positive stress cycles make you strong. After each cycle, you perform better. Negative stress cycles make you weak and lose. You will lose your strength. Right? So these positive stress cycles are very similar to the drain cyclic behavior of soils. Whereas the negative stress cycles are very similar to the liquefaction behavior of soils. Then I would like to discuss about the pressure dependency. This test is a very unique test. So what it does is, when you load a soil specimen, it has a certain confining pressure. The pressure comes from the surrounding. We call it the confining pressure. So the test began with a confining pressure of 100 kilopascal, and in the middle of the loading it is increased to 200 kilopascal. Suddenly the confining pressure is increased, and you can see, so it jumped into another level. This is the stress strain behavior under 200 kilopascal confining stress. This is the stress strain behavior under 100 kilopascal confining stress. So when you suddenly change the confining stress, soil response change accordingly. Higher the confining pressure, higher the strength or performance. Same thing happens to humans also. So peer pressure, right? Peer pressure can be both positive and negative. So I'm not going to go into the classifications. There are some spoken, unspoken peer pressure, direct, indirect, and positive, negative peer pressure. So there are scales developed by the psychologist, peer pressure scales, so many scales are there. And these scales are mostly developed to assess the peer pressure of undergraduates, right? So I will show you some such scale. Some events, right? And you have to give a kind of ranking to the event. How strong is the pressure from your friends to study hard? So it's a positive peer pressure, right? Or to not study or do your homework. So if the peer pressure is a lot towards this side, you have to give -3. If it is more towards the positive side, you have to give +3. Similarly, so many such tasks. Okay, you can see some items, right? Go and partying with the students, so drink beer or liquor, go to school, dances, so many such things. This is developed for undergraduate students. And you have to give a mark or score. Finally, take the summation and we can get an idea about the effect of the peer pressure on our the behavior. So positive peer pressure always make you strong, and negative peer pressure weakens you. Then finally, I would like to move into the post-peak behavior, what happens to the soils and humans after the peak. So the soil, the stress strain curves, it can have one of these, like even after the peak, the stress strain curve of some soils are like this. It keeps on increasing. We call it strain hardening behavior. And some soils have perfectly plastic behavior. After the peak, the strength remains constant. And in some cases, after the peak, you will lose the strength. And the most general type is a combination of all three. So you will see some strength hardening, strain hardening, and after the peak, some strain softening, and finally it comes to perfectly plastic state. We call it residual state of soils. Dense or over-consolidated soils show some strain softening. And there are high sensitive clays. The strain softening is quite significant. After the peak, you will lose all your strength. You are completely down. So loose sand or normally consolidated clay, you can't see clear residual state. After the peak, the strength remains constant. So similar behavior can be observed, like loose sand or NC behavior is like doing a simple task. So your performance increases with the stress level, but it's a simple task and your performance remains more or less constant. But if you are doing a complex task, you will undergo either dense sand or high sensitive clay behavior. After the optimum level of stress, you will lose your strength. Then what happens after the peak? So thixotropy is a very interesting characteristic. It is the gaining of the lost strength with time. So when the soils are disturbed, it loses its strength. Much of its strength is gone because you disturb it, right? Then if you remold it, it will gain some strength with time, but most of the time you will not get the original strength. So if you, after remolding, if you can get the original strength, such materials, such soils are called fully thixotropic soils. If the strength is gained partially like this, so this is the strength of undisturbed. When you disturb it, you will lose the strength, and if you remold, it will gain some strength, but not the original strength. So such materials are called partially thixotropic soils. Almost all the soils except coarse large size soils containing large size particles show this kind of behavior. Then humans also show thixotropic characteristic. The emotional response, or we can say the performance of the humans during some catastrophic event, right? You will see heroism, strength, anxiety, disbelief, disorientation, but your response is strong for a short period. Then you will start losing it. Discouragement, fatigue, stress, blame, anger, rage, sadness, grief, all things come into play. This is post-peak behavior. So it happens within 1-3 days. And within 1 to 3 years, you will gain the strength back. There can be some, downfalls due to the anniversaries of the event. Because during the anniversary, you always recall the bad memory. So it will make you weak. But the general trend is to gain the strength. And at the end of the day, you will gain maybe the original strength. It depends on the character. Some people get the original strength, or some people becomes even stronger. Some people will come to a certain level of strength as soils. So that's all about my presentation. I have discussed about some aspects of soil and human behavior. I don't have any conclusions or anything as such. But I have to acknowledge a few individuals. Please allow me 1 minute to do that. First, I would like to acknowledge my parents. So they always create a positive peer pressure on me, and as a result, I became strong, and they guided me to become who I am today. Then I would like to thank my family for converting all my daily hassles, micro stresses into uplifts. And they create a drain cyclic environment at home so that after each stress cycle, I became strong. It doesn't mean that I used to release my stresses through them. Okay. Then I would like to thank my mentors, Professor Kulatilaka, Professor Jayasinghe, Tishan Jayasinghe, and Madam Chinta Jayasinghe, and my colleagues and all my teachers and my colleagues, particularly Professor Nawagamu and Professor Sujiva Lewangama. They always create a positive peer pressure. Sometimes Professor Jayasinghe used to load me in an untrained manner, but somehow I used to cope with it. Positive peer pressure, and it create a drain cyclic environment at the university, and it helps me to unleash my full potential both professionally and academically. Thank you all for all your support. Thank you. And especially I would like to thank all the listeners who are joined through Zoom. I have received some overwhelming response for my Facebook post on this inaugural lecture. Thank you all for joining.
So I would like to thank Professor L.I.N. de Silva for sharing his insights about the similarities between soil and human behavior under stress. Sir, your presence here today is truly an inspiration for us, and we are grateful for your contribution towards our lecture series as well. And with that, I would like to invite Professor Chinta Jayasinghe to hand over the token of appreciation to our speaker. And once again, I would like to invite Professor L.I.N. de Silva to accept the token of appreciation. Thank you so much. So ladies and gentlemen, as we draw to a close on this lecture, we hope that you have found this lecture to be informative, engaging, and valuable for all of you. Remember, learning is a never-ending process, so we encourage you all to seek opportunities to expand your boundaries of learning. And finally, for all those who are present here and for all those who are joining us online, it has been an absolute pleasure for all you are to hear. We wish you all the very best in your future endeavors. And that brings our inaugural lecture for an end. And signing off, I'm Manusha Bevikrama.